This is 17.3 is titration. Notice that you have different colors here for the indicators. If you've done this in class with me, we would have done this at some point, probably trimester 3, which means no, you haven't done this yet. But titration is when we have something called a burette, which is a long, skinny piece of glass that has markings on it that are very accurately measured. And what you do is you have an unknown here in the Erlenmeyer flask of some concentration of acid, and then you use a base like sodium hydroxide, typically is what's used, in the burette, and you allow some amount of the base to be into the acid, to get into the acid and change the color, an indicator, and that will tell us how much acid that we have in the Erlenmeyer flask that we've used before. So pH meter, when we use a pH, that will determine, because we're talking about an acid-base reaction, we can keep track of the pH and know how far the reaction has come. So that's basically what a titration is. If you're in my class, if you're physically in the class, we've been working on titrations in class. That's not something that's easy to do outside of class. Okay, let's keep moving here. So take a look at this. This right here is like how we track the titration of using a pH meter by adding a strong base to a strong acid. And notice that in the first part of this, that this line is almost horizontal. So that means that the actual, oh, there it goes, way offline. So the actual pH is not changing much at all while I'm adding the beginning parts of the base. And then when the amount of acid and the amount of base in moles gets closer and closer to equaling each other, notice that the curve to the pH then takes a wild swing upward. So a very small amount of added base will change the pH an extreme amount. And right there is our equivalence point where the acid equals the base. So this is very important. Equivalence point means acid equals the base. For a strong acid, strong base, this should happen right at pH of 7, which means that they're both neutralized. There's no more, not more base than there is acid. Okay, so once we go through here, it's going to show us another picture of this. As it goes through to the other side, we have our, in this case, it looks like the acid is hydrochloric acid, and our base then, when it reaches the equivalent point, means that what we have are water molecules floating around and chloride and sodium ions floating around. And that's where our base, our equivalence point, is at 7. So there we go. And then past that, notice that after the equivalence point, it goes up very quickly, and then it starts to level off again. So adding more and more base does not actually do much. Now, here's why phenolphthalein can be actually a very good indicator for an acid-base titration, is because when we get to any part of the purple from here to here in the pH from 8 to 10, what happens is we go from maybe 50, if you're taking a look down here, the number of milliliters, we can go from 50 milliliters like this to 50.05 milliliters, literally a very, very small amount, and that might push you all the way through this range here. So phenolphthalein works great for this because the indicator right here is what we call the endpoint, when the indicator shows up as a color, and the equivalence point, and these two here, the endpoint and equivalence point, are very close with the amount of base that you add. So that's totally fine that we use phenolphthalein for strong acid, strong base, and for weak acid. So here it talks about how it goes through exactly the same thing. Acid, moles of acid equals moles of base. I just went through and explained all this, so I'm going to keep moving here. So let's go to the point where we get to a weak acid and weak base. So unlike the previous case, the conjugate base and the acid affect the pH. So that means that if I have HAC and then on the other side I have AC minus that's being produced. This affects the pH. It actually increases the pH of our solution, which means that our equivalent point is now going to be higher than 7. That's the only difference between a weak acid and a strong acid titration, is that the equivalence point is going to be higher, which means the end point is still pretty close to the same. So right there, equivalence point and end point are very similar, much closer than the strong acid, weak acid, versus the weak acid. Phenolphthalein is still commonly used. Here's the important part. Whenever we do these calculations, we always do our stoichiometric calculations first, as far as like we subtract, just like with the common ion and buffer sample problems, we subtract the base from the acid moles first. We subtract those two because they react, and then after we get the amount of acid that's left over, that's when we do our equilibrium calculation. And if we're looking for pH, if pH is what we're looking for, then we can use our pH equals pKa plus the log of the base, concentration of the base, divided by the concentration of the acid. Okay, that's our Henderson-Hasselbalch equation. Okay, so let's keep going. Now, the only other thing I want to talk about is what if our Ka, now take a look at acetic acid. Our acetic acid Ka is right around here because it's times 10 to the negative fifth. Okay, so that means that coming through here, notice our equivalence point is going to be somewhere right around, if it comes up through this way, somewhere right around there in the middle. Okay, so it's going to be above 8, which is what we expect. This is just a diagram to show how different Kas. Notice that if it's Ka of 10, negative 10, 10 to the negative 10, that there's not much of an equivalence point at all. It just kind of goes straight into being all base. Okay. Titration of a weak base. This is a strong base up top here. The weak base would be here. Notice it does the same thing but in reverse. Notice that the equivalence point is below 7. That makes sense. The equivalence point moves down past 7 because obviously the conjugate acid then makes a difference. So let's continue on. We're not going to do weak bases very much, definitely not in the lab. Polyproduct means that there's more, poly meaning more than one proton, and proton means hydrogen in this case. So if it's H3PO3 as a weak base, then you'd come up, the first hydrogen that we'd lose would have an inflection point right here. Continue on, the second hydrogen that we lose would have an inflection point in here, and then there would be one more for the last hydrogen. The last one, though, doesn't seem to, for this acid, doesn't want to seem to be lost at all. So this one only has 2 inflection points. Usually you have as many inflection points as you do protons. So I bet there are 3 inflection points for H3PO4 that tends to lose the last hydrogen before the end of the pH scale. Okay, that's it.